Hi everyone, it is time for the last keynote session of CVMP 2020. My name is Armin Mustafa and it is my pleasure to introduce our keynote speaker, Angjoo Kanazawa. Angjoo is an assistant professor at UC Berkeley and a research scientist at Google. She is very well known for her research and reconstruction of dynamic scenes with a special focus on humans and animals from a single image or video. And her talk will give us an overview of her latest research in this field. Please post questions on Discord in the Keynote channel, which I will pick up later after the talk. And I'm really glad that Angjoo is here to join us today. Let's welcome her. Over to you, Angjoo.
Thank you so much for the nice introduction, and thanks for having me here. I'm very excited to tell you today about the kind of work that we've been starting at my lab at Berkeley. Most of the research starts on this premise that we live in a world that is three-dimensional. So when we look at this picture, we don't really think of this as, lots of 2D people floating on top of each other, but we immediately perceive a scene where there's this hallway that you see that people are walking on, and these multiple people that are on the screen, like these two gentlemen, you don't really think of them as standing on top of each other, but these two people actually exist in this three-dimensional space. The man in blue is closer to us than the one in red. So there's this underlying scene that we can perceive from just a single image, and that is the world that we happen to live in. And this world also turns out to be dynamic, and it's full of life, with humans and animals interacting with each other and the environment, and a lot of things that's happening that we'd like to perceive from video. Okay, and then this challenge of 3D perception, that like although we see everything, perceive the underlying 3D world from a single image, what we actually get to see in our retina is always only a 2D projection. So how do we actually recover the underlying 3D scene just from a projection? This is a really fundamental problem that we study that I think has a lot of, is really fundamental, but also has lots of implication in the application and the way we will do things in the future. As we approach a society where intelligent systems and humans coexist, these approaches must be able to perceive and interpret and interact with people and the environment that might be dynamic in this 3D world. And so I think this is a lot of key. And I will show you a lot of applications, which I hope, I guess I don't really need to convince the audience here, but let's look at some of the successes. So there's obviously lots of success in multi-view 3D reconstruction, but this type of world method is restricted to the rigid world. So today we can reconstruct the city of Rome really well, but it would be lifeless without any people in it. And so how can we really go and capture these kind of non-rigid objects? Okay. So today's non-rigid 3D solution for this is really motion capture. It's practical. And I think most of the people in the audience would know about this, where you go into a studio, you have lots of cameras around, and you wear these special marker that allows you to get this 3D motion. Now, this is really a remarkable technology that we have it at the commercial level today, but it is not accessible for every consumer or creator. It would be challenging to take this system to everyone's living room. It's just not easy to or accessible for everybody to use. Moreover, the world is so much more than a green screen or a motion capture lab. The real world is very rich. It's difficult to really synthesize. And so one of the goals in my lab has been to do 3D perception from images in the wild. And in the wild is a jargon that we have in computer vision, which means that the images are captured in an unconstrained environment. So not like a motion capture lab, but from your phone, images or videos on the internet. Those are called in the wild. So that's that kind of images that we want to do 3D perception on. And that's the type of research that we've been conducting, where from a single image, you might recover a person's mesh, and the images might be from everyday photos with lots of clutter or occlusions. Or we might try to do this from video. Of course, the world is not just with humans, there's also animals. And so much of my research is about how can we actually reconstruct animals using a similar approach. And hopefully today I will give you some insight to this. And then these approaches, of course, you can print it and do all of these cool, fun graphics applications. And lastly, we're also looking into recovering more detail of the person, including the clothing and the surface from a single image or few images. So in this talk, really, I will give you an overview of the space to just recap the method in which you might recover these non-rigid objects by taking human as an example. And I will, briefly go through the method. And then I will touch upon, what is happening with animals, really to talk about what makes animals more challenging and interesting, but also a lot more challenging. And then I want to talk about. I will end with new directions that I think are exciting in this space. Which really is going towards the full scene 3D reconstruction. So from this image of people in the park, you can reconstruct the humans and the objects. And then, of course, you want to really get not just these underlying abstract representations, which are useful for a lot of applications, but also one that can capture these surface details. Okay, so let's quickly talk about the potentials that these things can have. So obviously, if you can recover these content from a single image, it has a lot of accessible tools for 3D aware content generation, so that people can make these effects from every creators. Another application is things like these 3D portraits from everyday photographs that today we need to go into a scanner to scan. Of course, a mixed reality application that actually understands what people are doing and how they're interacting with objects has a lot of potential. Not only for graphics, but if you wanted to understand what people might do, as for example, for systems like self-driving car, it's important for them to understand what human motion is in the 3D world from the observations. Recovering fine-grained motion is still very challenging, but if we could do it, it would make these biometrics more accessible to people, which is today only available through an elaborate motion capture setup at a big hospital. So that's another direction. Of course, ability to recover animal motion really helps you. Oh, well, there's a lot of application in animal science and ecology, and so that I think is high impact. Is really challenging, and of course, the ability to perceive the underlying 3D world has a lot of fundamental applications that lets you to do things like this baby who is imitating the motion of the actor in the scene, and so this is very useful in terms of animations or creating new animations, but also building the system that can learn like babies from watching people. And eventually, hopefully, we will get to a system that can interact with humans and its environment. Okay, so there's a lot of potential, but let's talk about why this is a hard problem. And as you may know, well, this is a challenging problem because 3D is always we only get to look at the 2D projections, and so we basically lost one dimension, and in doing so there's many possible solutions that can explain our current observation. So this is really what makes this underdetermined nature of this problem makes it really challenging. That's the first challenge. So let me give you an example. So I have these I will show you two shapes that equally explain these 2D joints, and then as far as the 2D joints are concerned. So the first one looks like this, which you might just expect. The other one looks like this, where the person's knee is bent on the other direction. And so which one is the correct one? Of course, it's the one on the right. And the reason why we know this is because our knees don't bend in this weird direction. And so the reason why we could resolve out of all of the million possible interpretations that would both explain these 2D joint observation is really because we have this knowledge of what a human body is like from our past visual collective experience. We build this very good knowledge prior of the world, and we are really using this to understand the image. So at the high level, a lot of the methods that I employ really take this framework, or mostly lots of, I mean, any machine learning in general, but in specific, the idea is that you want to have a model of the non-rigid objects. Okay, and so this is like idea of what human body is like. And then a very abstract level, what we're doing is really fit this model to the images or the observations. So you get this image, and through this model, we obtained the explanations by the model that best describes the observation. And in that case, that might be, most likely solution. So that's really what the model is, and really the central questions are, how do we obtain this prior? Like, what does it mean to fit this model to an image? How can we do this? And there are many different ways to do it. So a classic example from a classic computer graphics literature is that of Blantz and Vetter from SIGGRAPH 99, where they collected lots of 3D faces, and then they learned a morphable model of a face. Once you have this kind of forward model, you can use that to fit it to image observation, which turns out to be pixels in this case, with differentiable rendering back in 1999. So right, the key questions that you could look out for if you're interested in this world, in this area, is, how do we learn this prior, or the model of the world, and how do we fit this model to the observation? What kind of observation do we need in order to fit this model? Is it the pixels, or is it more like 2D correspondences with the pixels, 2D key points? And what kind of supervision do we need to really put this system together? So these are different aspects of it that you may want to kind of keep in mind. But let's just start with the case of humans. And for humans, we are special in the sense that we can actually ask us to do a lot of things, and we're cooperative. And so we have lots of scans of people. And from this, you can actually build this model of the human bodies. So this is a very nice model that a lot of us use from Michael Black's lab at MPI. So this model is called simple skinned multi-person linear model, and the idea of it is a linear blend or a model with a morphable model of a shape. And so you have this low dimensional 10-dimensional subspace that by changing you can change the shape of the person, like their height. And then it also has an embedded kinematic skeleton of 23 joints with three 3x3 rotation matrices, which is expressed as an axis angle over here. Which when combined, you can use linear blend skinning to move the mesh of the skin of the person according to the kinematic skeleton, which gives you this control to generate any kind of mesh with the kinematic and this shape of the person. Of course, we're always taking a picture, so let's throw in the camera parameters, 3 for rotation and 3 for translation. In this model, so the first part is this idea of what the human body shape is like. And the second pose parameter captures what human kinematic structure is like. Together, these, if you just sum the numbers of parameters, these add to 85 dimensions, 85 numbers that define the body in the image to some degree. And so all of you have some 85 numbers if we were seeing each other in person, or even through your Zoom pictures. And then really the $1 million question is, how do you recover this 85 numbers from an image? So that's what we looked into when we developed the first fully automatic single view 3D human mesh humans in 2016. And here the approach is really more classic optimization, similar to the Blantz and Vetter model that we saw. But first of all, given an image, what you do is you use these off-the-shelf 2D pose detection algorithms like OpenPose, which work really well these days, to get an automatic 2D joint detection. And the goal is to fit this model, solve for pose and shape that explain the 2D joints. And by solve, I mean we were going to set up some optimization algorithm where the goal is to minimize the reprojection error, which is basically 3D joints. When you take a picture, where does this go? And you want it to go on top of the 2D joints that you have. And so here is an animation of this optimization from initialization to the end. So you can solve for the parameters of the model that really best fit the data. Of course, this is still under constraint, so you still have to put lots of priors. We will see later. So this is one of the first approach to recovering a human, which is to do this optimization, fit this thing. Okay, and so there are a couple of problems, which is that this method is only looking at the 2D joints and not the image, so you throw away a lot of the information. And then this is an optimization-based inference, so it's too slow for video. It takes about a minute or so, and so it's difficult to scale up to lots of video. So then, now in this day, the question is, why can't we just throw a deep network at this? It's like image in and 85 numbers out, right? Like, how difficult can this be? This is actually really difficult because in order to train these deep networks, you need lots of supervision. But images in the wild, like this picture's image, this is actually a reconstruction from the optimization process. It's not like we actually had the ground truth 3D pose in the shape of this person because we couldn't have captured this person. Right. And so there isn't any ground truth image. So what are we going to do? So in summary, the challenges are that there's a lot of depth ambiguity in this problem, like multiple 3D joints explain the 2D joints. And then there aren't that many data. There are a lot of data sets that are collected in a motion capture data set, like in green screen. But when it comes to data sets like COCO, it doesn't have the actual corresponding ground truth 3D. So the lack of ground truth 3D data for 2D to 3D labels, that this is a real challenge, and there are many ways to go around this. One of the solutions that we did in 2018 was to have this observation that even though a lot of the images don't come with ground truth 3D, there's a lot of unpaired labels. And so by this, what I mean is I have lots of images with 2D key points. They don't have any ground truth 3D, but on the other hand, I've also captured lots of people. There's lots of data on this. So that really serves as a prior to learn what the poses of people can be. And so what you do is ask the network to explain the 2D observation while staying within the distribution of these real body poses. And this leads to the human mesh recovery method, where the idea is you take an image and you predict these 85 numbers, which gives rise to a mesh. And if you had the ground truth, you will use it, but you don't have this for images in the wild. So instead, you use this reprojection loss that we just discussed, which is take a picture of these 3D joints, make sure that they overlap with the 2D annotation. So this is nice because you can actually now train this model with 2D joints alone. But again, I told you that this is a very underdetermined problem. So if we're only looking at 2D joints, we're going to get a lot of monsters like this, where it minimizes the 2D joints, but it clearly doesn't look like real people. So in order to avoid this, we can use that repository of scans of human body to kind of give you an idea of what are the possible parameters of the pose. And you can formulate this in an adversarial framework where you send this to a discriminator, the latent parameters of the mesh body model, and identify whether it's a real human or not. And this nicely regularizes the solution to stay within the manifold of real humans. Okay, and at test time, you can just run this network. So it just feed forward. And so it's a lot faster. And you can train this on images in the clutter with just 2D key points. And so it's more robust to these kind of setup. Now, I do want to talk about this latest approach from Kostas Danilis' lab, which I really like, which takes these hybrid solution. So, again, you have this image in a CNN, and that's what we were just doing, this prediction. And the problem was that there is no ground truth on this image. This is why we had to come up with a lot of these ways. But this approach combines the first approach, which is the optimization approach, with this second, the direct prediction approach. So you predict the human, you use that as the initialization, and then you solve that optimization problem. Now you actually have this optimized 3D mesh, and then you can just use this as a training loss for the network. And you don't really need to backpropagate the signal from the optimization. You can just treat the solution of the optimization as a word of God that came to you for your network, and you just train your CNN with this actual ground truth. It's not a ground truth, but pseudo ground truth 3D supervision, and this cycle really can benefit each other and then improve itself. So this is a really nice approach that is more proposed recently, which goes around this problem of not the lack of 3D data. Anyway, these are all single image approaches, so you can run them on video. And then they look okay, but they look okay per frame, but they lack temporal coherency. So the next question is, how do you actually incorporate time? And I'm not going to get into too much detail, but really the idea is quite simple. You just take the approach that we just saw, which was HMR on single image, but now you also add a temporal convolution so that the network can take some temporal context into account. So for every single frame, we're going to use a similar network to extract some kind of latent representation. And then we're going to have this for every single frame. Now, instead of asking the 3D mesh from each of these frames, we're actually going to do another temporal convolution that aggregates all of the information and contextualizes it and makes it into another latent variable. And from this, we simply ask the same question of what is the 3D mesh. And we also actually ask, what are the nearby body motions, because it encourages the network to pay attention to the temporal context. You can just train this in exactly the same way that we did. If you have 3D, you can use it. And if you don't, you can just do 2D with this adversarial prior. So this approach allows you to recover, here's some video. So on the left is a model that is single frame only. And the one on the right is the one with the temporal context. So it's a lot less jittery, and it incorporates these time. Yes. Okay, so one caveat that I want to say if I'm giving a talk here is that when you look at a lot of these human mesh recovery methods, that's a lot right now, you want to be asking, what does that result look like from the other viewpoints? So let me demonstrate, because both of these results look quite good on the viewpoint from the video. But when you actually look at it from a different viewpoint, you notice that the single frame approach, even though it looks okay in this view, you can see that it's a lot more jittery. Maybe the video is not very good, but you will see that it's not that good. So it's just a lesson. Whenever you see a result from 3D human mesh recovery or any type of 3D method, ask the authors or in the paper, look for the other viewpoint, because that's really what tells whether it's working or not. Okay. All right, so there's a lot of cool applications that you can do from this. So we can actually take a step towards this baby who is imitating this Rocky video. And so clearly he's perceiving it. And so the approach that we just talked about gives you perception on the 3D joint angles of the human body. And so that's nice, but really that's not the end of the story, because once you perceive it, that's very different from actually actuating the muscle to get to those poses. And control is not easy, as demonstrated by this baby who's trying to imitate his dad and is getting there. I need to train his control algorithm a little bit more. So prior work on this, bypass perception and start from motion capture and use a reinforcement learning approach. So the question is, you will have a character that you want to simulate, and you have a reference motion capture. The character requires actions, but the reference motion is only a recording of joint angles. So it doesn't actually tell you what kind of actions you have to take in order to get to that pose. And so this is why you can formulate this in a reinforcement learning framework and then train this simulated character to perform these actions. Okay, but the problem is that this is happening in the motion world, motion capture. So let's expand the world to video. And this we can do because now we can actually recover the 3D body from video. And then using this 3D body, you can train the policy on top of it. And so this is a really nice aspect that comes out from using this parametric model where there's a lot of interpretability. Not only do we get the 3D mesh, but we also get the joint angles. And this is very useful for these tasks. This is necessary for training this kind of model. And then this is this is not just copying the recovered 3D joints, but it's also interacting in this physical simulated world. So you could interact with it. You can also try to do this in a different character. And then my favorite result from this work is the one where we taught Atlas how to dance from watching YouTube videos. So here are some summary of the learned skills. And okay, all right. So that's one. Another really nice thing about the video is that once you have this video, really you can do dynamics prediction, as in there's future is already in the video. If you want to know what is this person going to do in 5 frames, you actually have that information in the video, because you just play 5 frames and that's what's your target. So you already get this supervision of what the future is going to be in a self-supervised manner. And so you can use this, quite literally, this idea to train an autoregressive system that, given a video, can predict the future motion of the person. Hope this video is showing. Yeah, and so this only from an image video you can predict the future. I'm just showing the actual future for reference. Here's another example. Okay, where it learns to shoot the ball. All right, so that's really covering a lot of things that we can do with humans. Now, you might be asking, well, it's not just humans, what about other deformable objects? Of course, like cats, well, how can we actually use this to reconstruct cats? Actually, a similar kind of approach can work, where you take a template model and you want to deform it, and so that it can actually match the 2D key points that you see in an observation. But of course, this is a really challenging problem for many different reasons, on top of the humans, on top of the challenges that are already available in humans. But this is what I want to talk about. So what is the challenging and very interesting thing about animals? Well, really, the core is a lot more limited availability of data in all aspects. Animals are hard to bring into the lab and 3D scan. They are a lot less cooperative, and so it's a lot more effort to capture them. Also, especially these wild animals might be difficult to bring into your lab. And so basically there aren't that many 3D scans or motion capture. Furthermore, there's also a limited amount of 2D labels, as in there aren't any data sets like Coco for humans, where we have lots and lots of video images of lions with their 2D annotations. And of course, a solution that we can see foreseeable that seems like it's working, which is to annotate the 2D key points of every single animal species. But this is obviously is very hard to scale and it's somewhat unsatisfactory. How can we really do this without having to do that? And another real challenge is that animals have a lot more diverse shape. Humans have shape variations, but what are we going to do with elephants or giraffes? Okay, and so this really puts the animal problem in this low data regime of the machine learning problem. How can we learn from just a small amount of data? And this is really an interesting direction and in the real challenge. And that is actually something humans are very good at doing, or so we think, because we don't really need thousands and thousands of examples in order to learn a concept. Okay, and so this is really interesting problem in machine learning. And also, I think this is a problem with a lot of impact because being able to track animal behavior has a lot of impact in or like a lot of use in neuroscience, understanding animal behavior, and also being able to track and understand animal behavior from images has a lot of application in ecology and so forth. So I hope more people gets into this space. But let's take an example of the reason why this is really hard. Taking, for example, this nice simple model that we had for humans was built on this like lots and lots of scans. And this is something that we can't really do if we wanted to do it for, say, lots of kitties. The kitties would be surprised if we had something like this. And so we don't have this for animals. And so real scans are limited. And even synthetic scans are also limited. And so this is a couple of years ago, but when we were on TurboSquid, there's a lot more scans or 3D models of chairs than those of cats. And so that's also limited. So a direction that we've been pursuing with my collaborators, Sylvia and Michael Black, has been really to one thing that we looked into was, we might not have lots of scans of 3D animals, But we have a lot of these. We noticed that there's high quality toy animals for children that are available on sale. So if you're a parent, maybe you might know. And so what we did was we hand scanned this set of animals and then obtained this 3D scans of these animals. And there are only 30 scans or so, so there's still not that many, you know. But now that we have these 30 scans, we can actually align them, which is actually quite a challenging problem, and then learn some kind of shape model. So, you know, to give you a brief, you know, taste of it, what we have to do is align every single animal. This is a really challenging problem because every single animal is in a different pose and shape. And so Sylvia had proposed this very nice part-based models that can be deformed to fit to every single scan. And this can be used to register or align every single scan, meaning that means solving the correspondence as shown here by the color. You know, the same color indicates correspondences, and you can see that they are all in correspondence. And once you've solved the correspondence of them, you can put them in the same pose and then learn a shape space. And so this is what we result that this is what came about, which is this low dimensional space that you can change, where you can walk from one animal to another animal species. So I think we had 5 in this data set. And of course, we also had a kinematic tree that is once defined by humans, and an artist embedded, and so you can also animate them. So now this is how we have the model. So now you can actually fit this model to images. Of course, you need to have some kind of observations. And unlike humans, we don't have open pose for lions here. So we have to manually annotate these 2D key points and silhouettes. But once you have them, you can again take the same paradigm, take the model, and then fit it to the observation with lots of priors. And so this way you can recover these nice 3D models of lion. And here are some other animals that we've reconstructed in this work. And in the follow-up work, Sylvia also shows how, if you had multiple images of animals, the small model, because it's a low dimensional model, it tends to be a smooth representation, but you can embrace the traditional knowledge of idea of space carving from these multiple images once you have recovered these poses and shapes, and obtain a much more accurate shape. Get fine-grained, detailed, high-frequency shape from this. And once you have a more detailed shape, you can actually extract texture from these multiple views, and then texture the model also. And so that is really nice thing about this approach, which is that given multiple view, you can extract this texture map of this tiger, and then you can just see it in from different viewpoint. And if you look closely, you will see that the textures come from different images, so there might be some differences in the lighting, but it still makes a compelling kind of reconstruction. So this is nice, but the caveat, of course, is that in order to do this, we had to have manual key points and segmentation annotation for every single image. And so we can't run this on something like video because it's a lot more time consuming. But although I do want to mention that we do have this kind of approach available today. So as long as you're willing to annotate, you can actually run this. And we just open sourced this code like earlier this year. And so this is a nice tool for artists if you don't mind it. But obviously, we want to make this a lot more, less manually intensive. And so one approach that we looked into with animals is that of sim-to-real. So you can use this particular approach, we call it smaller, to reconstruct the zebra images, and then obtain a texture map. And once you run this on a couple of zebra images, you can actually create a synthetic data set of them, because now you have texture. You can slap them on random data sets. You can do these, make this synthetic data set where you actually have the ground truth. Once you have the ground truth, you can train a similar kind of model that is a deep network that directly predicts these 3D model and a texture map from a single image. And now you can actually run this on and then that can run it on a zebra video and then obtain this kind of zebra 3D reconstruction pose. So, we've demonstrated this on zebras. And this was a collaboration with Tanya Berger-Wolf, who studies these animals, and it's a working example. But really, there's a lot of question that remains. There's as to how to scale this. What if we had limited scans? Like, what if the animal that we're interested in, for example, was like an elephant and wasn't in the original set of scans, so it's not covered in the shape space in a significant way, not just not having horns for the rhino, but and what if we never got to see any 3D models? Can we learn a 3D models if we only get to see 2D images or video? That's really an interesting question. And then I won't discuss this, but there are other directions that I study, which we study, which is given this image collections, without ever seeing ground truth 3D shape of a bird, can you actually reconstruct the bird shapes and also learn the model at the same time? And so really the frontier of this direction is going in the question of how can we do 3D reconstruction without 3D models or even any 2D key point supervision. And so this is also one of the work where the results from one of the papers which does not rely on any 2D key points. And so this is really at the forefront of unsupervised 3D object pose recovery, where we want to be able to do these things without much labels. Okay, so that is animals. And so far, I've kind of covered how we approach this problem of humans, and also gave some directions about how we would do this for animals. And so what is next? We can keep on making these approaches better, but what other aspects have I not really explored, and that aspect that I think is exciting? And I think that is really going towards a complete 3D or even 4D, which is more ambitious, but let's say towards complete 3D scene reconstruction. And so this is what I am thinking about, which is so this is one of the more recent work that we proposed at ECCV 2020 this summer, where the goal is to reconstruct humans and objects in the wild together, as shown here. And so this is the problem of recovering the 3D spatial arrangement of the humans and objects. Oh, I see. I am missing one key slides for this. Oh, here, let me see if I have this. Okay, I don't. All right. Okay, well, that's okay. Because it was trying to demonstrate how difficult this problem is. So given this image, right, this is really what you expect. And it's obviously this is the right answer. Like, why wouldn't the person be riding on the bicycle, or sitting on top of this this bench? So this other slide that I had would have shown you the other many interpretation of this scene, which really you will see a little bit later, which will where the person is floating in the air and they're not on the bench. And so a naive reconstruction of each of these objects alone, independently, will give you many solutions, and that might not be corresponding to the thing that you really expect. And so this is a fundamental scale ambiguity that exists in 3D to 2D that we discussed, but in particular with humans and objects, it's really severe. So given this image, okay, of this human and a surfer, the surfboard could be there or could be there, but so it could be a small surfboard that is close to the camera or a large surfboard that is far away from the camera, and they equally project to the exact same 2D image that we see here. So these renders are obtained from both of these surfboards, and they look exactly the same. And this is because in this line of sight of the camera, there are infinitely many possible 3D interpretations of where this object can be. And so, when you go beyond analyzing single objects, but look into how humans and objects interact with each other, this is yet another ambiguity that you have to deal with. And there's a couple of ways to disambiguate. So for one, we might have this common sense prior, which is that we know that surfboards aren't so small, and we also know that surfboards aren't going to be twice as big as a car. So we have some expectations which you can use, but you also have human object interaction prior. If you know that the person is riding the surfboard, then you know that it has to be touching the humans legs. So this is the kind of intuition that we incorporate in the optimization process. So the overview of this approach goes as such. So given a single image, you can reconstruct these people using these approaches that we discussed, which treats each person independently in a box. And then you can also recover the objects by fitting an existing 3D CAD models to these semantic segmentations, which works surprisingly well. Or there's more to be desired, but it works well enough at this stage. And then if you independently compose this is the one that I'm trying to say. If you look at it from a top down, you will see that there's a lot of weird reconstructions where people are floating in the middle of the, not really on top of these objects. And so but you can use the priors that we just discussed earlier to do some global reasoning, and so that you can obtain a 3D reconstruction that satisfies these kind of priors of how humans interact with the world. So that's what we've done, and this is some of the results that we obtained from the COCO data set. And obviously, this is in the wild, and there's no ground truth 3D for these things. So it's interesting to see how far these optimization approaches can go. And really, the future is really taking this far away, taking this to the limit, and then recovering the entire environment along with the people and the whole scene in motion inside that scene. Okay. The other direction that you may have noticed is that this entire time I've been showing a lot of these parametric models, which gives you this very nice insight about the structure of the human body, but it doesn't really capture the appearance of the person. And so really the next direction is the full appearance capture, the full digitization of the person, including the clothing and the hair and the accessories. And also the texture. And so this is an approach that from a single image, this is obtained from a single image. This approach is also mindful of the potential way you might use this, which is that, not only if you want to do high resolution capture, maybe you don't have just one image, but multiple images. And the more images that you get, the better your reconstruction should be. This approach is also designed so that this is it can do both single images or multiple images, which is an important point because a lot of the methods are only designed for single images or only designed for a specific number of views. And so you want to have that kind of flexibility. And to give a very brief insight into this, how does this thing work? Well, so this approach builds up on this implicit functions, which you may have heard today. It's very exciting right now in deep 3D deep learning, where you use implicit functions. Like you might heard something like NERF. So this is similar. So for a single input image, this is a volumetric approach where first you obtain some convolutional image encoding from this, and for every single 3D scene, you really want to ask, is this particular point inside the surface or outside the surface, and compute something similar to this continuous sign distance function or occupancy field. And so the idea is you take this point and then you project it to an image, and then you have this point in the image, and then you extract that same 2D point feature, okay? And then you also know how far away this point is from that particular image because you just projected it. And so you're going to ask a network that takes in this pixel aligned implicit function, as in the feature that corresponds to the particular pixel, not a global representation, because if you do that, you lose a lot of the detail. And so that was really the point of this paper. which is you can take these two things and ask the network whether this particular point represented by this depth over here is inside or outside. And this is what we call PIFU, pixel line implicit function. And this is because it's an implicit function, we can ask more than just 0 or 1 of inside or outside. You could be asking what the color is at that particular point. And this allows you to get this kind of surface. And the nice thing about this approach is that it is, unlike voxels, which is also a volumetric approach that people explored earlier on, it's a lot more memory efficient. There's no discretization issues, and it preserves local detail because our approach is fully convolutional with this spatial alignment. And more than anything, it can handle arbitrary surface topology that a parametric model may not have been able to. So this is all these nice things. Unfortunately, this particular approach needs 3D supervision, but we just released this recent paper called PixelNerf, which gets around this approach, which is also inspired by PyFu and NERF, that you could train a system like this from just image reconstruction loss. So that's some exciting development, but I'm not going to talk about it today. This approach works surprisingly well. And then even though it's trained on this synthetic data set, it generalizes to these kind of real images of photographic or like fashion type images, including these, accessories. And so this is very hopeful. And then, all the authors, we've reconstructed all of us from a single image. We've even, done a 3D portrait of this. And there's a lot of work happening in this space, follow-up work from the authors, which to make it high dimensional, or also latest reconstruction have made it into real-time capture. So yes, I just covered a lot of things, but really a bottom line is that this is an exciting time to be working on 3D perception from images and video. So I would like to end here with my image that we reconstructed. And so I think the vision of the world is going to be one where eventually we can just reconstruct this kind of the entire scene, but each one of these people are you will know their high level abstract representations, but also have their appearance, and it will be a full scene capture, and hopefully they will be moving around that you can go in and have this immersive experience. And so before I end, I very much would like to thank all of my collaborators and students without whom I can't do any of these things. So thank you very much, and thanks for your attention.
Thank you for an amazing talk, very impressive results. I'll just check the Discord for questions. I think we have a few questions on Discord. So the first question is by Juan. He's asking, what do you think about transfer learning, the machine learning based models between animals? So this is the first question.
Yeah, that would be really interesting. I think, one thing that I'm really excited about is like, you have all of these different animals. The thing I didn't really get into it is that reconstructing them, okay, so I said that this is very difficult because you don't have 2D pose. But even if you have 2D pose, the 3D pose is still ambiguous. You still have the problem of the monsters, right? And then this is where I think the cross-category transfer is a really exciting problem. Like if say you have a motion capture of a dog, which is something that's actually available today, can you use that knowledge to also use it as a prior for giraffe or elephant? Like they're all quadrupeds. How do we actually kind of go across morphology, or they actually have some similar morphology but like different shapes, and we should be able to generalize that kind of knowledge. So how do we do that transfer, I think, is really the question when it comes to animals. So animals is where you have all of these legitimate like machine learning questions. It's not like I'm just gonna pretend I don't have these labels to I actually don't have these things. And so I think this is why it's a really exciting problem to test these things out. Yeah,
definitely. So the second question he has is, how far do you think we are from high quality markerless capture system?
I think for animals, I mean for humans, it's really kind of getting there. I mean, I think it really depends. Like how if you were, I think if you really cared about high quality, I would say you probably don't mind having multiple shots of people. Like if it's cooperative, I think it's coming there. But like this pilot results, I was blown away when I first saw this result. I was like, I mean, it's a single image, and so it was something I didn't think was possible, but the development is happening a lot. I would say this is already real time, and so for humans, I would say we're getting there in like 2 years or so, or a year or so, in the level of photogramming, like a photorealistic, say, avatar. Yeah, but motion is really hard, especially
Yeah.
fine grained motion. And so hopefully we will see similar kind of advances, but we will see. Yeah.
Yeah. I think his last question is, do you think it would be necessary to rely on physics-based simulation models as prior for dynamics? I think this relates to your comment on motion.
Yeah,
Also, yeah.
definitely. Exactly. Yeah. So that's, yeah. So certainly. So this is why, actually, this is a good example, because if you play this video, you will see that this like perception-based model still has some issues. Like maybe you don't see it because of the video, but the motion from the policy certainly looks a lot more natural and fluid. And this is because this is a simulated environment with physics, and so physics really acts as a regularization to get rid of the terrible ones. And so I think there are a couple of recent works that was presented at ECCV from Adobe and Christian Thielwald's lab that does incorporate in the optimization process. I showed you the reprojection, but one of the lots of priors could have been these physics. And
Yeah.
so I think that's certainly a direction that people are already going. And for animals, for example, maybe this is the way you can expand the possible set of 3D dynamic prior.
Yeah.
Except, yeah, right now it takes a little bit of a time, and I think that's the problem with these approaches. Yeah.
So Manuel has another question. I think this is related to your FOSA paper. How do you enforce coherent connections between objects in a scene in order for a model to learn them? So I think this is for the FOSA paper, the last but one work. Yeah.
Right. So yeah, so I didn't really get into the details of this work, but really this is actually just an optimization based approach. And so there's no learning per se. Like you use the learning out of these out of the box, but it's really kind of exploring what kind of common sense knowledge that we can integrate in this system, like that, if you know that this human and object is interacting, they should be touching. And so it's kind of using that kind of prior in the optimization process to resolve the ambiguities. And now that you have this, if you recall all of the developments, once you can fit the model, then you have lots of pseudo ground truth, and you can actually train a predictive model on top of it. And then there's this kind of hybrid approach where the feed forward approach is able to give you better initialization, and therefore optimization is better. And so there's this kind of cycle. But this model in particular kind of relies on human baked knowledge. So for example, we bake in things like, these objects should be touching the feet, like the bottom of the feet are places where you could touch them. So it does take the advantage of that knowledge. And another interesting approach is to learn that kind of affordance information from an image or video. Like how would a human interact with this object, and then learn that from interaction. So that's another learning question that happens.
Yeah, but it looks like it requires a lot of manual intervention to feed all this information, right? To make sure that the objects are aligned with the person, because the wherever the person body touches the different objects, we have to kind of highlight those parts of humans and objects both, right? This is what I understand.
In this one we kind of paint the 3D models of where, but actually, this is somewhat of a labeling, but it's much better than having to label every single image. and like say whether this is. So that's the nice thing about a 3D model. Like once you actually have a 3D model, you just label and paint the model once, and that would work for everything. And so
Yeah.
that's one, advantage. But yeah, certainly, I think the interesting direction is, how do we actually learn this kind of interaction from just data?
Yeah, but I think that's the most difficult part, right? To bring this optimization framework to a learning framework and trying to learn it in as less data as possible. Actually, you have done a lot of work with only 30 scans in for animals. I'm sure there will be something which comes up and solves this problem as well.
Yeah.
I have one question on the PyFu paper. So the results look amazing. I think uh, this is one of the main advantages of implicit function, right? That
Right.
you get high quality reconstruction from a single image.
Right.
But what are the limitations? So I know that one of the limitations is like you require 3D reconstructions to train the network.
Mm-hmm.
For example, can it work for different poses of humans? Uh, I know handstand wouldn't be possible. If a person is doing handstand, it won't work. But what happens when you have like various poses for humans in the same?
Yeah, it's a good question. So yeah, because this currently as is, it requires 3D supervision. It was really restricted to this really nice photogrammetry, like captured data set of humans. And so the poses outside that, it's not going to work. And so this is mainly demonstrated on like more simpler poses. Although like maybe some, but exactly if you did some kind of like breakdancing or things like this, it's not going to work.
Yeah,
Another kind of caveat of these approaches that not that many people might think about, which is that these implicit functions or can capture arbitrary topology, which is really nice, but that really
yeah,
means that you also lose the correspondence between every single person. It's really just like a
yeah,
scan. And once you scan,
yeah,
you still have to do these registrations. So I think a new challenge in future is like how can you take advantage of both of these parametric models where it's very interpretable, but you still
yeah.
add this implicit surface on top of it. And there's some work in this direction already. Uh, I think that's one another thing. Yeah, and then in terms of this 3D supervision, yeah, that's our recent work that I didn't talk about called Pixel Nerf that we just put it on archive like a week ago. Is trying to get to that. Yeah.
Yeah. Okay, I'll wrap up I'm aware of the time, so I'll wrap up the session here. Thank you once again for your amazing talk. We are really glad to have you here.
Thank you.
And thank you so much once again. I wish there was a clapping thing, but unfortunately, there's no. Anyways, thank you, Angjoo.
Thank you so much. Thank you for hosting me. Thank you.